Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I am going to go over the first law of thermodynamics. And once again, I did go over this in an earlier video, but in this video I want to review a few things and tie it to more of thermodynamics and energy systems. So to remind ourselves what the first law of thermodynamics is basically that it is the law that all the total energy of the universe is constant. So there's no loss of energy at any one moment. All energy is transferred or changed into another form, going from one form to another. So there's a couple of things that we have to keep in mind is this idea of internal energy. Now, in the last video, I misspoke and I said that the internal energy was the kinetic energy of all the particles in a system, and that's partly true, but I didn't mention the potential energy as well. So the internal energy is the sum of the kinetic and potential energies of all the particles that compose a system. And this is really important because, especially in chemistry, if the system is going to be a reaction, then we gotta pay attention to the particles of the reactions as well. So we have the the products and the reactants and things like that. So that's going to be important. Um, and the other idea that we need to keep in mind is this idea of a state function. And a state function is basically a value that only depends upon the state of the system. What does that mean? It means that it doesn't depend on how you arrived at that state. It's just what the state is. So here's an example. If we think of energy, the internal energy of a system, so delta E, is a state function. It doesn't matter how you got from one state to another. All it matters is what the state you started with and what's the state you end with. So the change in the energy is going to be equal to the final energy that you started with, or the final energy that you end with, and the initial energy that you started with. That's it. It doesn't matter how you got from the initial energy to the final energy. It just matters what you started with and what you ended with, and that's it. What path you took. For example, in a chemical reaction, it doesn't matter if you used an enzyme or not, right? So if you used an enzyme to go from reactants to products, the energy change is the same whether you use that enzyme or not. So that's kind of like what they're getting at with respect to like the how. The how doesn't matter. It's just what you start with and what you end with, and that's the idea of a state function. Also, if we understand this idea of internal energy, and we understand that the energy of a system is dependent upon the final energy and the initial energy, then when we understand it as a reaction, then the delta E of the reaction, the change in energy of the reaction, if the reaction is our system, is going to be the energy of the products minus the energy of the reactants. So we're starting with reactants, right, that have a certain amount of energy to them, right? So internal energy, again, depends on the kinetic and potential energies of the reactant. So potential energy is something that you should be thinking of when you hear potential energy. You should be thinking of bonds, right? So the potential energy between atoms is like in the bonds. Also, so if you're thinking about the total sum of the kinetic and potential energies of particles, then if you're thinking of the delta E of a reaction, then you're thinking of the energy of the reactants before they react, so that's going to have a certain amount of energy. And then you have the products, the end, right, after the reaction is complete, and that's going to have a certain amount of energy. And so the difference between the energies of the reactants and the products is going to give you the change in the internal energy of the reaction, which is normally your system, right? So if we have a diagram like this is called an energy diagram. And so depending on where your reactants are, so if I have reactants A plus B, and I go to, let's say, C plus D, if my reactants are higher in energy than my products, then the energy change, right, if I go this way, if these are my reactants and these are my products and I'm going this way in the reaction, then I am losing energy. So the delta E of the reaction is going to be negative, right? So the products minus reactants. So my reactants have a higher energy than my products. So when I subtract, it's going to be a negative amount. And that negative amount is important because that tells us what's going on. So it tells us, the negative tells us that the reaction lost energy. The reaction is our system. So the system lost energy. So energy would go out of the system. Well, if energy goes out of the system, well, where does it go? It goes into the surroundings, right? So the same amount of energy that's lost by our system, the reaction, is picked up by the surroundings. So they're both equal in energy, but they're opposite. So whatever the system loses, whatever our system is defined to be, which is usually going to be a reaction, whatever energy that loses, it's gained by the surroundings. And the opposite happens. So if I'm going this way, right, if these are my reactants and these are my products, then the reactants start out lower energy. And then what happens is that when they go up in higher energy, then what happens is I'm going from low energy reactants to higher energy products. Well, I gained energy. That's how the products gain energy. So somehow I gained energy. So in this case, energy is going into the system to give the products higher energy. So in this case, the energy gained by the system is positive, and then the same amount of energy is lost by the surroundings. So the surrounding is losing the same amount of energy. And that's what this equation here is representing, that the change energy of the system is equal to but opposite of the change energy of the surroundings. So this is going to be very important. Also, one of the things I want to point out is this idea of work. So work can be treated like energy, so heat. So the change in any system, the internal energy, the change in the energy, internal energy of the system can be determined by a change in heat, Q is for heat, and a change in work. And so you can think of work in the same way as energy. So work can go into a system, work can come out of a system, kind of like in the same way that energy can go into and out of, right? It just depends on what is doing the work and what is the work being done upon, right? So if, for example, if I have a balloon and I heat up the balloon and the gases in the balloon expand the balloon, then the gas, let's say that's my system, the gas inside the balloon is pushing up against the balloon, making the balloon expand. So in that case, the gas is doing work on the balloon. So if the gas is my system, then work is being lost, or energy is being lost by the gas in the form of work. So it's doing work on the surrounding container, which is the balloon, right? So in that case, the system, which is the gas, is doing work on the surroundings, which the balloon is part of. And so in that case, the system is losing energy through the work it's doing, right? So that would be negative for work, right? So you can do heat and work together. right? Another example would be if I'm squeezing the balloon, right? So, or if I put pressure on the balloon, I am doing work on the gas inside the balloon, right? So in that case, I'm part of the surroundings. I am squeezing the balloon together, so I'm doing work on the gas. So in that case, work is positive here because I'm doing work on the gas in the balloon, and so therefore work is being received by the gas. So that would be positive, and so that's going to add to the change in energy. So it's going to make the energy change be positive, right? So I have to look at both the heat and the work being done. If the work is zero, then the only thing I need to look at is heat. If heat is zero, then the only thing I need to look at is work. But if I have both of them, then I have to look at both of them and to see what the overall change of the energy, the internal energy of the system is going to be. I think that's all I wanted to cover in this lecture. I hope that was clear and helpful. If you like this video, like the video, share the video with your friends, subscribe to the video, and make a comment in the comment section and let me know what you think, and let me know if there's anything else you want me to go over. Thanks for joining me, and I'll see you next time.